This video will cover the Friedel-Crafts alkylation. The Friedel-Crafts alkylation is an electrophilic aromatic substitution reaction where the electrophile is a carbon. Therefore, the reaction results in a new carbon-carbon bond. This reaction is catalyzed by a Lewis acid. In this case, Rx is an alkyl halide, where X is equal to chloride, bromide, or iodide. The Lewis acid is typically aluminum trichloride or iron tribromide. The mechanism for this reaction is similar to other electrophilic aromatic substitution reactions and only differs in the formation of the electrophile. The exact mechanism for the formation of the electrophile depends on the substitution of the alkyl halide, whether it's methyl, primary, secondary, or tertiary. If the alkyl halide is secondary or tertiary, the electrophile is a carbocation. The carbocation is formed through loss of the halide from the alkyl halide. The Lewis acid acts as the electron acceptor. If the alkyl halide, though, is methyl or primary, a stable carbocation cannot be formed. Therefore, typically the electrophile is a complex of the alkyl halide with the Lewis acid. In this case, the Lewis acid still acts as an electron acceptor. However, the bond between the carbon and the chlorine, in this case, does not break fully. Instead, a partial positive forms on the carbon attached to the chloride and a partial negative on the aluminum. It is this entire complex that serves as the electrophile. Now, let's look at the mechanism for this electrophilic aromatic substitution reaction. This video will show only an abbreviated mechanism, without all of the resonance contributors to the sigma complex. Make sure that you feel comfortable writing out the complete version on your own. In the case of a secondary or tertiary alkyl halide, first the carbocation is formed as shown previously, and then the carbocation reacts with the aromatic compound. This forms the sigma complex. In the final step, the sigma complex is deprotonated by the aluminum tetrachloride ion to reform aromaticity. In the case of a methyl or a primary alkyl halide, the complex between the alkyl halide and aluminum trichloride is formed as shown previously. This complex reacts with the aromatic compound. This forms a sigma complex, which is then deprotonated by the aluminum tetrachloride ion to regenerate aromaticity. Again, remember that these are only abbreviated mechanisms. The complete mechanism shows both the generation of the carbocation, or alkyl halide aluminum trichloride complex, as well as the formation of the sigma complex, all resonance contributors, and the deprotonation of the sigma complex to reform the aromatic final substituted product. Finally, we will consider the limitations of the Friedel-Crafts alkylation reaction. First, the Friedel-Crafts alkylation reaction does not work with strongly deactivated systems. Remember that strongly deactivated systems include benzene rings that are substituted with groups such as the nitro group, the sulfonate group, or the quaternary amine groups. Consider, for example, this reaction. If we treat nitrobenzene with isopropyl chloride and aluminum trichloride, no reaction will occur because the deactivated benzene system of the nitrobenzene is not enough of a nucleophile to react with the Friedel-Crafts alkylation electrophile. A second limitation of the Friedel-Crafts alkylation is that because we're typically working with carbocations, carbocation rearrangements can occur. Additionally, it is important to note that even though the Lewis acid alkyl halide complex that is formed in the case of primary or methyl alkyl halides can also rearrange, even though it is not a true carbocation. Let's look at an example. If we treat benzene with this alkyl halide and aluminum trichloride, we will get the following product, which results from rearrangement. Initially, the electrophile that is formed looks like this. However, a simple hydride shift can create a much more stable carbocation. This is the carbocation that results in the product seen. The final limitation of the Friedel-Crafts alkylation reaction is that the products of the Friedel-Crafts alkylation are activated compared to the reactants. Because they are activated, they react more quickly in further electrophilic aromatic substitution reactions. Therefore, this can lead to overalkylation when using the Friedel-Crafts alkylation. Let's look at an example. Consider if we want to make this compound, ethylbenzene. We can make this compound by treating benzene with ethyl chloride and aluminum trichloride. However, after even a small amount of ethylbenzene is formed, this compound is considerably more reactive to further alkylation than the starting benzene molecule. Therefore, the ethylbenzene is more likely to react with the ethyl chloride and aluminum trichloride, giving mixtures of products. In order to circumvent this problem, we typically keep the concentration of benzene high, which makes it much more likely that benzene will react with the ethyl chloride and aluminum trichloride than the products, which are low in concentration as the reaction progresses.